name is Birgit Mertens, and I'm working as a scientist at CNSANO, the Belgian Scientific Institute for Public Health, where I'm responsible for the service Risk and Health Impact Assessment. Within this service, we have different activities, and one of these activities includes the development and the implementation of new approach methodologies, also referred to as NAMs, into the chemical risk assessment process. It is with this background that I will present to you today some challenges, but also opportunities regarding the implementation of NAMs in the risk assessment process. But first of all, I will provide you some background on why, despite the different challenges that I will discuss later, it is very important to continue with the implementation of NAMs in the chemical risk assessment process. So, first of all, it's important to better understand the legislative framework. Within Europe, Directive 2010/63 applies regarding the protection of animals for scientific purposes. And within this European directive, it is highlighted that wherever possible, an animal test should be replaced by methods or strategies that do not directly entail living animals. So very shortly, when it's possible, you should replace the animal test by something else. So this is the principle of replacement. However, in case replacement is not possible, the principle of reduction, but also the principle of refinement applies. And reduction means that you should limit animals to a minimum, but the minimum of animals should still allow you to provide you sound scientific evidence. But also, as I mentioned, the principle of refinement applies, and this means that the pain, the discomfort, and the stress of the animals should also be reduced. As a consequence, we can due to this directive, there is really a legal obligation to apply the 3Rs principle and thus to reduce, where possible, the animal test by a method that does not use animals. This general framework, this general legislative framework regarding the protection of animals, there are also more specific restrictions. For example, it is no longer allowed in Europe to use animals when evaluating skin corrosion potential of a certain compound, but also it is not allowed to use primates for testing of chemicals. And very importantly, there's also a specific legislation with respect to cosmetics. And I will focus a little bit more into this legislation because the regulation of 2009 with respect to cosmetic products was put in place to really emphasize that animal testing should be phased out for cosmetic purposes. And this was very important because this also offered a framework for the development of new approach methodologies that could just be used instead of the animals that were no longer allowed for these cosmetic products. Now, when we talk about new approach methodologies, we talk about different types of methods. These include, for example, in silico methods. In silico methods refer, for example, to computational methods, modeling, read-across methods. But new approach methodologies also refer to high-throughput screening and imaging bioassays. They can also include advanced imaging, scanning techniques, omics applications, cell culture, so when using 2D or 3D systems, but also more complex in vitro systems, such as tissues and organ engineering, and that may lead into the generation of, for example, organoids or organ or human on a chip. And in some definitions, as you will see later, also alternative in vivo models, such as, for example, a fly model or C. elegans, are considered new approach methodologies. When we look into the definition of the new approach methodology, as I already mentioned very briefly just on the previous slide, is that multiple definitions are available. So, for example, ECHA and US EPA use a certain definition where they refer to new approach methodologies as any technologies, methodologies, approaches, or combination that can provide information to support chemical hazard and risk assessment and avoid the use of intact animals. However, there is also the definition of EFSA, and they refer to the new approach methodologies really as non-animal based approaches. And then finally, there's, for example, also the definition of Health Canada, which stays a bit more general and says that NAMs include alternative methods to bridge the transition from conventional in vivo studies to in vitro assays that satisfy the 3R criteria. So it's important to highlight that also illustrated on this slide. Currently, we do not yet have a formally accepted definition of new approach methodology, so of these NAMs, and therefore it's always very important to clearly indicate or to clearly refine what you mean with a new approach methodology. Are you really referring to methods that do not make use of animals at all? So also not of animal-derived material, which is sometimes a bit tricky because in certain cell systems, you still use animal-derived material, for example, to mimic the metabolic fraction, or do you refer to methods that do not use intact animals? And then these, or do you also want to include lower in vivo models such as the zebrafish embryo, etc. So overall, it's very important to clearly define what you are referring to when you talk about the NAMs. So now I will focus a little bit more, first of all, on the different opportunities that the NAMs offer. So these NAMs, of course, will support the implementation of the European Directive 2010/63, because by developing more and more of these NAMs, we will just also be able to more and more replace the animal tests. On the other hand, in most of these cases, these new approach methodologies make use of human-derived material, and therefore they can even better mimic the human situation than some They also allow to provide more insights into how certain vulnerable populations, for example, might react to a certain stimulus, such as exposure to a certain chemical. Moreover, as I also mentioned on the previous slide, when showing the different NAMs, we see that there are a lot of high throughput techniques. And of course, these allow to have a much faster readout and a higher throughput compared to the animal testing. And this is also very important, certainly when we consider that we still have a lot of chemicals for which we don't have data at the moment. And so by having a higher throughput, we are just also able to generate this information in a much shorter time frame. But of course, the use of NAMs is also associated with some challenges, and I will walk you through each of these challenges a little bit more into detail. So the first challenge is the regulatory acceptance of the new approach methodologies, and this is associated, or which makes this so tricky, is often the lack of trust in these new NAMs, because as indicated in the name, they are new, and everything that is new always generates at the beginning some hesitance, some reluctance maybe. And also, of course, if we have something new, we need training to better understand exactly what type of information these NAMs are providing. So let's focus a little bit more on this aspect. So when we talk about the NAMs, often these are the newer technologies, so they are high throughput, they are generating a lot of information, which is much more complicated and much more complex than the data that we currently, for example, retract from our in vivo studies. And of course, the interpretation of these complicated data sets is not only time consuming, but it also requires a very specific expertise. And not all regulators, so not all the people dealing with these data can have the expertise in this wide variety of NAMs. Moreover, if you have this large amount of data, and often also includes really molecular data, it is not always clear how relevant these data are for, in the end, an adverse outcome in humans. Here, there are also solutions in the making to help to better understand how then the complex data set relate to the human situation, and I will come back to that later. And on the other hand, it's also often unclear how the data interpretation should be done. And sometimes also no harmonized methods are in place to do the interpretation. And this makes it for regulators also very complicated how they should deal with the data. Now, to facilitate regulatory acceptance, it is important that we have some standardized methods. Because if we just have a compound and we want, for example, to know if it is inducing mutations, so whether it's mutagenic or not, and we are just going to send this compound to 3 different labs and they all do their testing and they come back with different results. And of course, the question is, which of these results can we trust? And therefore, we have standardization needed, because if we know if the testing is done according to the standardized method, we can rely on the results. And this is something that's very important for regulators, that they know that when they receive the results of a certain test, that the test has been in a kind of way standardized and validated so that they know that the results are reliable. A second aspect, and it's also a very important tool, is how to then perform the methods really in practice. And here we have a guidance document on good in vitro regulatory practices, and there they really provide information on what it's important to consider when you develop a method, but also when you do then the standardization and the harmonization. So the different levels are there described. What should you take into account when selecting your cell system where you want to work with? How do you need to do the practical work and so on? And again, this can help not only for the method developers, but then also later for the regulators that will use the data of these methods to have more confidence, more trust in the results generated with these tests. A second point is the validation and the standardization of the NAMs, because these processes are very slow and complex. So on one hand, I mentioned that regulators, in order to increase the trust, they require some validation, standardization of the NAMs. But as I can show you here on this slide, the processes to do this validation are very complex. So they take a lot of time. So once you have your method available, when you just have developed it, and then you want to come to really the results of this method being used by regulators, it takes a lot of time. It's really an extended process. So this is something that is also really a hurdle for the NAMs. It's also not only time consuming, but also really money consuming. And certainly as a method developer, the development is often done at academia. There is not really an interest to invest a lot in this validation process, at least not an interest from a real scientific point of view, because just repeating the test with an additional number of compounds, that's not so interesting to publish. So in that sense, there need to be an extra value for you. For example, if you design a spin-off company, so you can then later on perform the test for external partners, there might be an interest. But otherwise, it's very hard for people to continue with this validation process, because also at the beginning, of course, you have no guarantee that your method will come out successful of the validation process. Now, also to have a better understanding on what the validation status of a new approach methodology is, you can have a look in the TSAR system. That's the tracking system for alternative methods towards regulatory acceptance. So you can access the tool via the link provided over here. And then you can see for a certain, typically toxicological endpoint, you can see then whether there is a method available, at least what the status of a method of interest is. Now, I mentioned, so the validation is a very long, extended process requiring a lot of resources. What there's currently also ongoing is already in an earlier stage, so during the development or just after the development, doing a kind of readiness assessment, so that also for regulators it is more clear in what status of readiness, regulatory readiness, and method is at a certain time point. And there are different ways to do that. There are different tools. So there are, for example, the tool of Ball and Price that you can see over here, which requires a lot of detailed information. And then based on this detailed information, it gives you an indication on whether the method is quite close to regulatory readiness, regulatory application, or whether it's still far away from this. But there is also another tool. This is shown over here. That's the method readiness tool that was originally developed for specifically endocrine disrupting evaluating methods, but can also be applied to other methods. And there the tool is a bit easier. It's an online application that you can fill in. And then you get as a readout these spider diagrams, which also give you an indication about the readiness, the regulatory readiness of your method. So the more you're on the outside, the more ready your method is to be used by within a regulatory context. So these tools can also help certainly for regulators to better understand, okay, we have a new method, might be promising, but do we still have a long way to go for regulatory use, or is it already far developed? Then another hurdle is that NAMs can also NAMs can also trigger animal testing rather than reducing animal testing, because of course with all these new methodologies, with this higher throughput and so on, we can look to effects and endpoints that we have not investigated before with the more traditional in vivo testing. So this means that we can have additional information and that need to be then explored further in an in vivo setting. So we need to be careful also here that the NAMs that we develop in the end will not really trigger a lot of more animal testing. So here also careful consideration is needed. And then another thing is that, of course, ideally, what we initially thought was, okay, we have one animal test and we want to replace it by one of the new approach methodologies. But in most cases, this is not possible. So when we talk about this one-to-one replacement, and we have some examples of that, and mainly for local toxicity, for example, in order to investigate irritation, skin irritation. Initially, the Dreyse skin test was used in rabbits, but here we have a good example on how this in vivo test, which was really causing a lot of pain and discomfort for the animal, could be reduced by alternative or new approach methodologies that do not use animals. However, in most situations, it is far more complex. We cannot just replace the animal test by one in vitro test or one in silico test or whatever, but we need to have to work with a combination of different assays. And one way to do this is by making use of integrated approaches to testing and assessment. In fact, these IATAs, what we also can be seen as pragmatic science-based approaches for chemical hazard characterization, and they integrate on one hand existing information with new information, and this new information is preferably generated with new approach methodologies. There are a broad range of IATAs. We have the more flexible approaches, but we have also the more structured, descriptive, rule-based approaches, which we refer to as defined approaches. So very briefly, what's the idea behind the IATA? So overall, the first step is to start with a clear problem formulation. So you should very clearly define what the regulatory question is that you would like to address. Then you start gathering existing information, and you can then see, you evaluate whether with this existing information, you're able to address your regulatory question. If this is not the case, So if you cannot come to the regulatory conclusion, you will have to generate additional information. And as I mentioned, preferably you will do this with new approach methodologies. You again do the assessment, the weight of evidence assessment. Do I now have sufficient information to come to a regulatory conclusion? Yes, then okay, that's solved. No, then again, you can see, is there additional information that I can generate with new approach methodologies? Or do I in the end still need to go to in vivo testing to come to my conclusion? Now, in order to select the different IATAs, the different tests within the IATA, one concept that can help a lot is the concept of adverse outcome pathways. And I will show you one example, and that's the IATA for skin sensitization, how the concept of the adverse outcome pathways was used to develop an IATA for skin sensitization. So when we think about skin sensitization, without going into the details, there are some key steps. So first of all, your chemical or compound of interest needs to be bioavailable in the skin. Then in the next step, it needs to be able to bind to a protein. And then there should lead to epidermal inflammation. Then you will have activation of the dendrocytes, there will be migration, and in the end, there will be T-cell proliferation. So these different steps can be translated into what we call an adverse outcome pathway. And so such an adverse outcome pathway, what's very typical for this adverse outcome pathway is that they link a molecular initiating event to an adverse outcome, and they do this not by describing every detail that is happening between the molecular initiating event and the adverse outcome, but instead on focusing on some of the key events, so the most important events between the molecular initiating event and the adverse outcome. And so these key events for skin sensitization are exactly the steps that I mentioned on the previous slide. So what was done then? So the different key steps were translated into these key events. And if you do that, so in fact, what happens is that covalent binding to skin proteins, so your molecular initiate event, is then via some of the key events leading to the adverse outcome, so the skin sensitization. And once you have this, you can then map different in vitro assays or in silico assays to the different key events. And so the in vitro and in silico methods will be mostly linked to the more upstream, so the earlier key events, whereas for really detecting the adverse outcome, we normally need the in vivo test. Now, by doing this, so we get a better understanding which type of information the in vitro and in silico methods are providing us, and also how this information in the end tells us something about the adverse outcome. So this was done. So we had the adverse outcome, we had the different key events, then the different new approach methodologies were mapped to the different key events within the AOP. But then we came to a situation that many different combinations of NAMs were possible. And then for the regulators, it was again very confusing, because which of these different combinations is now then giving you the best answer. And in order to overcome this problem, defined approaches have been designed to skin sensitization, and these just provide you a fixed combination of different tests. And they say if you use this combination, this set of tests, they can replace the animal test. So that is what we call a defined approach. So compared to the IATA, there are some differences. So in fact, the defined approach can be seen as a specific form of an IATA. So the IATA is designed really in response to problem formulation, whereas the defined approaches are really designed to address predefined endpoints or predictions. So in this case, really focused on, for example, on skin sensitization. So I will not go into the details. There are, like I mentioned, important differences. Overall, what's the most important is that the IATA is more flexible, is judgment-based, whereas the defined approaches are more prescriptive, sorry about that, and rule-based. And of course, regulators give a bit more preference to such defined approaches, because then it's much more clear how they need to deal with NAMs and data generated by NAMs. So yeah, just to come back then to this scheme, in fact, when we are talking about the defined approach, we want to reduce the level of expert judgment and to make it more fixed, so that it's more straightforward to come to a conclusion. So to end with, I would like to emphasize also that within Europe, a lot of initiatives are currently ongoing to really further stimulate the implementation of this new approach methodologies in chemical risk assessment, and just trying to overcome the different hurdles I mentioned before. And one of the frameworks in which this is done is the PARC partnership. So that's the partnership to assess risk for chemicals. That's a public-public partnership funded under the Horizon Europe call. There are more than 200 partners involved within this PARC partnership. And by working together, the aim is really to consolidate and strengthen European research and innovation capacity for chemical risk assessment, in the end, with the goal to protect human health and environment. And the main goal is also to stimulate the transition towards next generation risk assessment, with a central role for the new approach methodologies. So hopefully in the next years, we will be able to overcome some of the challenges that I mentioned in this presentation, so that we can really obtain this goal, and to have at least for some endpoints a situation where we do not have to rely on animal testing anymore, but instead that we can work with new approach methodologies. So that was it from my side. I hope you have learned something, and that you have now more insights on why these new approach methodologies are so important, and that we really should continue the way forward to implement them into the chemical risk assessment. And in case you have some questions, you can contact me on the email address displayed on this slide. Thank you for listening, and bye.